So friends, today we are going to discuss a new problem which is based on the shear force and the bending moment diagram. Okay, and this has been asked in IS 2012. Now friends, see this, how we will approach this problem. This load of 8 kN is acting at a point of 1 meter from this point. So because of this 8 kN load acting at this point, okay, there will be a movement about this point and it will create a concentrated movement which will go in anti-clockwise direction and have a magnitude 8, the magnitude of this load into this distance 1 meter. So 8 kilonewton meter will be the movement created at this point because of this load, and this movement can be further transferred to this point and it will act here at this point C in anti-clockwise direction. So this movement is transferred here, so I am rubbing this movement, okay, the effect of this movement is transferred over here and the force can be transferred here. So rubbing this force from here of 8 kilonewton and transferring this force to this point C. So I am rubbing this force of 8 kilonewton, okay, and this extension 2 I am rubbing and transferring that 8 kilonewton force here at the point C. So the system will remain unaffected by doing this. So 8 kilonewton is also transferred at this point C, and moment because of this 8 kilonewton force is also transferred at this point C, and the magnitude of that moment was how much? 8 kilonewton meter. 8 kilonewton meter was the magnitude of that moment because of this force of 8 kilonewton. Now friends, we will draw the shear force and bending moment diagram for this figure. Now see this friends, how we will do this. First thing is that we have to assume the reactions at the point A. Suppose reaction at A is acting vertically upward direction like this, and reaction at B is also assumed to be acting in vertically upward direction like this. Okay, reaction at B. Now we know that sum of these two reactions is equal to net vertical load acting over this beam. So RA plus RB is equal to the net vertical load acting over this beam. So the net vertical load acting vertically downward is equal to 8 kilonewton acting in vertically downward direction, and this UDL will constitute a force of the intensity of this UDL, that is 5 into this span of 4 meter over which it is spread. So it will give us 5 for the 20 plus 8 is equal to 28 kilonewton. Okay, now friends, we will take the moment about the point A to be 0, that is moment about the point hinge is to be 0. Now because of this RB, there will be a moment of RB into this distance 4 plus 4 is equal to 8 from this point A, which will try to rotate this beam AB in counterclockwise direction, that is anti-clockwise direction about the point A, and anti-clockwise here is taken as positive. Now because of this UDL, there will be a moment of magnitude and having a negative sign because the load because of this UDL will act here in the middle at a distance of 2 meter from the point C, and it will try to rotate this beam element AB, the beam AB in clockwise direction about the point A, so taken here as negative, okay, clockwise rotation. And the magnitude will be the intensity of this UDL is 5 meter and the distance over which it is spread is 4 meter, and it will act at a distance of 2 plus 4, that is 6 from the point A. So it will give us the movement like this. Now because of this concentrated movement, it will rotate this beam element AC in counterclockwise direction. See how this is the point A and this is the beam, this is the point C, and this movement is acting like this, that is going in this direction counterclockwise. So this will try to rotate this beam in this direction about the point A. This beam element AC is being rotated by this movement in this direction, okay, that is in counterclockwise direction about the point A. So here counterclockwise is treated as positive, that is anti-clockwise direction. Counterclockwise means anti-clockwise, and anti-clockwise is treated as positive. So taking positive here of magnitude, what is the magnitude? 8 kilonewton meter. So 8 kilonewton meter. Okay, now friends, see, because of this force of 8 kilonewton, there will be a movement of magnitude how much? Minus 8 into this distance 4, because, and it will try to rotate the beam in about the point A in clockwise direction. So it is, when you substitute it to 0, then you can find the value of RB coming to be 18 kilonewton, and the value of RA will come out to be how much? 10 kilonewton. Now friends, we will solve this problem by solving the finding out the bending shear force at the point A, C and B. Now friends, we will find out the shear force at the point A, C and B, because at the point A there is a reaction acting RA, and at the point B there is reaction RB acting. At the point C there is a point load of 8 kN is acting. That's why we have to calculate the shear force on the left side and on the right side of all these points. Okay, because shear force will change suddenly from going from the left side of the point A to the right side of the point A because of this RA, and similar is true for this point C and B. Now we will find out the shear force on the left side of the point A. So for that you have to construct a section here on the left side of the point A. Now we know that according to the definition of the shear force at any section is the summation, algebraic sum of all the forces either on the left side of this section or on the right side of this section. So here we will choose the left side. So on the left side there is nothing lying, so shear force on the left side of the point A is 0. Now we will find out the shear force on the right side of the point A. For that you have to construct a section on the right side of the passing through the right side of the point A. So suppose this is a section constructed passing through the right side of the point A. Now looking on the left side of this section, only this force is acting at the point A and lying on the left side of this section. So it will contribute toward a shear force of magnitude 10 kN, and it will have a positive sign using this sign convention. Okay, because this is the section XX and this force RA is lying on the LHS of this section and going in vertically upward direction, and this is our sign convention section XX, and this is the beam element, and this force is lying on the going in upward direction and lying on the left hand side of this section. That's why treated as positive. Now shear force at the point on the left side of the point C we will calculate. So making a section here on the left side of the point C like this. Okay, now looking on the left side of this section, only this force is contributing toward a shear force of plus 10 using this sign convention. Okay, now using shear force on the right side of the point C, if you want to find out, then construct a section here passing through the right side of the point C like this. XX is constructed here. Now you can see this, friends. On the left hand side of this section, this force is contributing toward a shear force of plus 10 kN using this sign convention, and this force is contributing toward a shear force of minus 8 kN using this sign convention. Okay, this sign convention. So it will give us 2 kN. Now shear force on the left side of the point B we will calculate. For that again we have to construct a section passing through the left side of the point B. Suppose this is a section XX constructed passing through the left side of the point B. Now you can look on the right side now, because on the left side you will find a little bit difficult to find the shear force because there is a more calculation involved by looking on the left side. So I am taking here the right side. So looking on the right side of this section XX, you can see that this reaction RB is only accounting for the shear force and its magnitude is 18 kN. So 18 kN, and it will create a negative shear force using this sign convention. So negative shear force of 18 kN, and because this section is drawn very close to this point B, that's why this UDL is not considered in this case. Okay, now shear force on the right side of the point B will be 0, because on the right side of the point B, if you look, then construct a section passing through the right side. On the right side of the point B you have to construct a section, okay, like this. I am constructing on the right side of the P. If you construct a section like this, and when you look on the right side of the section, then nothing lies. That's why shear force is 0 on the right side of the point B. Now we will draw the shear force diagram. Now see this, on the left side of the point A shear force is 0, so making a cross here over the point A, and shear force on the right side of the point A is plus 10 kN, so making a cross here at a distance of 10 kN above the point A, and shear force on the left side of the point C is 10 kN, so making a cross here in the level of the this point at a distance of 10 from the point C, and shear force on the right side of the point C is 2, so making a cross here above exactly of this point C at a distance of 2, and shear force on the left side of the point B is minus 18. So on the left side it is going to minus 18, suppose lie somewhere here below the point B, and shear force on the right side of the point B is 0, so 0 lies somewhere here. So joining first point with the second point with a vertical line, because there is a reaction acting at the point A, and joining second point with the third point with a straight horizontal line, because there is no load line between the point A and C, and joining third point with the fourth point with the vertical line, because there is a point load lying at the point A at the point C, and joining the fourth point with the fifth point with the inclined line, because there is a UDL line between the point C and B, and again joining these 2 points with a straight vertical line, because there is a reaction RB lying at the point B. So this is our shear force diagram, and the area of this diagram is treated as positive, and below this line is treated as negative. So this is our shear force diagram. Now we will draw the bending moment diagram. Now friends, we will find the point at which the shear force is going to be 0. That is, suppose this is the point K. Okay, I am naming it as K. Now we have to find the point, the location of this point K, because at this point K the shear force is going to be 0. So for that, what we have to do, see this. We have to see these two similar triangles. This is the similar triangle 1. Suppose this is the first similar triangle, and this is the second similar triangle. Okay, now suppose the dimension of this similar triangle, that is the vertical height of this similar triangle, is taken as y1, and this distance, that is the base of this triangle, is taken as x1. Okay, and for this triangle, okay, the height is taken as y2, suppose, and this distance, that is the KB, is taken as how much? X2. Now from the property of the similar triangle, we know that friends, y1 by x1 is equal to y2 by x2. Now we know that y1 is equal to 2, okay, and y2 is equal to 18, and this x1 is equal to how much? X1 is not known to us, we have to determine, and x2 also we have to determine. But we know that, friend, x1 plus x2 is equal to how much? X1 plus x2 is equal to this distance, that is 4 meter. Why? Because x1 plus x2 is equal to CB, and CB is equal to 4 meter. So I write here 4 meter. So x1 is equal to, x2 can be taken as x2 is equal to 4 minus x1. And when you substitute the value of x2 here in this equation, 2 by x1 is equal to 18 divided by x2 is equal to 4 minus x1, taken from here the value of x2, you can find the value of x1 as, x1 will come out to be how much? You can calculate by yourself. The x1 will come out to be 0.4, and the value of x2 will come out to be 3.6. Okay, the value of x1 will come out to be 0.4, and the value of x2 will come out to be 3.6, using the property of these similar triangles. Now friends, what we have to do? We have to find out the value of the bending moment at this location K. That we will do later. Now friends, we will find out the bending moment at the point A, bending moment on the left side of the point C, and on the right side of the point C, denoted by these two terms. Why? Because there is a concentrated moment acting at this point C. That's why bending moment will change suddenly when going from the left side of the point C to the right side of the point C. And we have to find out the bending moment at B by this term, denoted by this term. So the bending moment at A can be found out by constructing here a section passing through the point A. Suppose this is the section XX constructed here. Now looking on the left side of this section, first of all we have to know the definition of the bending moment. The definition of the bending moment says that bending moment at any section is defined as the summation of all the moments either on the left side of a section or on the right side of a section. So here we treat the left side. So on the left side of this section XX, you can see that nothing is lying. So see, bending moment at the point A is 0. Now bending moment on the left side of the point C we have to find out. For that we have to construct a section passing through the left side of the point C. Suppose this is the section XX constructed here. Now looking on the left side of this section, this force is accounting for a bending moment of magnitude 10 into this distance 4, and it will create a sagging bending moment treated as positive using this sign convention. Okay, it will give us plus 40 bending moment kilonewton meter. Now bending moment on the right side of the point C, if you want to find out, then construct a section on the right side of the point C. Okay, so looking on the left side of this section, this force is causing a bending moment of magnitude how much? 10 into this distance 4, which will be sagging in nature using this sign convention, so treated positive. And because of this concentrated movement, there will be a bending moment of minus 8 kilonewton. because this concentrated movement is lying on the left hand side of this section. So because of this concentrated movement, the bending moment will be minus it. Why? Because using this sign convention, we can say that if a movement is lying on the left hand side of a section and going in anti-clockwise direction, it is treated as negative. Similarly, this movement is lying on the left side of this section XX and going in anti-clockwise direction, so it is treated as negative. And because of this force of 8 kN, there is no bending moment about the section XX. Why? Because this section XX is drawn very close to this point C, on the right side of this point C. So the distance of this 8 kN force is almost 0 from this section XX. So it will give us 32 kN meter. Now bending moment at point B we will find out. For that we have to construct a section passing through the point B, and looking on the right side of this section, you can look on the right side also. Looking on the left side will create a lot of problem because there is a lot of calculation involved in that case. So we will look on the right side of this section XX. So nothing is lying on the right side of this section XX, so bending moment at B is taken to be 0. Now friends, we will find out the maximum bending moment, which is occurring between the point C and B. That is, we have to find out the bending moment at this point K. Okay, bending moment at this K we have to find out. The point K is lying between the point C and B, and the point K is lying at a distance of 3.6, this 3.6 from this point B. Okay, so this point K will lie somewhere here. Okay, I am drawing here. It is lying somewhere here. So draw a section XX passing through this point K. It will lie somewhere here, the point K. And looking on the right side of this section, you can find that the distance of this section is x2 from this point B, this x2. So this x2 is the distance of this section XX from B. And at this distance x2, the point K lies. Okay. Now bending moment at this section XX we have to find out in order to find out the bending moment at this point K. So looking on the right hand side of this section, you can see that this RB is contributing toward a bending moment of magnitude RB, that is 18. The magnitude of RB is 18 into this distance 4, and it is creating a sagging bending moment using this sign convention. Okay, and the bending moment because of this UDL, which is lying between the point K and B, will be equal to bending moment at the point K, that is at this section XX, is equal to the bending moment because of this reaction RB, that is having magnitude 18, and it is lying at a distance of x2 from this section XX. So multiplying it with x2, and it will create a sagging bending moment using this sign convention, so taking positive. And bending moment because of this UDL, which is spread between the section XX and this point B, can be find out by subtracting intensity of this UDL is 5 into this distance x2 over which it is spread between the point B and K into the x2 by 2, that is the distance at which it is acting from this section XX. It will act as a distance of this, that is x2 by 2 from this distance from this section XX. Okay, and here sign is taken as negative using this sign convention. Okay, that is hogging in nature. Now friends, if you solve this by putting the value of x2 as 3.6, x2 here put as 3.6, here also put x2 as 3.6, you will find that the value of the bending moment at K is coming out to be 32.4 kilonewton meter. Now we will draw the bending moment diagram. The bending moment at the point A is 0, so making a cross here. Bending moment on the left side of the point C is 40, so 40 will lie somewhere here of the point C, suppose. And bending moment on the right side of the point C is 32, so it is decreasing to 32 somewhere here on the right side of the point C. And bending moment at the point K we have to find out first. Bending moment at the point B is 0, it is clear. Bending moment at the point K is 32.4, so 32.4 will lie somewhere in between 40 and this 32, that is here 32 above the point K, 32.4 you have to mark. Okay, so here it is lying here, suppose, and above the point K this 32.4 is lying somewhere here in between this, suppose 40. Actually I have taken wrong scale, you have to do it with selecting a proper scale. So suppose 40 was lying here, so 40 points, so 32.4 is lying somewhere here of the point K. Okay, 32.4. Now joining first point with the second point with a straight vertical line, because the shear force diagram is a horizontal line between the point A and C, and the second point is joined with the third point with a vertical line because there is a point load acting at the point C, and the next 2 points are joined with a inclined line, that is a parabolic line. Why? Because there is a parabolic loading between the point C and this point K. Okay, and the last 2 points are joined again with the parabolic line because there is a UDL line between the point K and B. So this is the shear force bending moment diagram. Also friend, the parabola is curving like this, that is curving in this direction because shear force is increasing as we go, shear force is decreasing as we go from C to K, and it is increasing as we go from K to B. So that's why parabola is curving in this way. This is all for today.